actually quantify the outflows. So we need to measure how much material is carried in them. We need to measure how fast they're moving and how much energy they're carrying, and see how that compares with these types of simulations. And the hinge pin is that this is a very difficult thing to do. Measuring these properties very precisely is quite difficult, and some of the previous techniques that have been employed may have very large uncertainties. It's not very well understood. So these are kind of the big questions and the route that we want to take. How are we going to go ahead and do that? We're going to use the two fundamental tools of astronomy. So the first is imaging, and the second is spectroscopy. So in imaging, we're just actually taking an image of a galaxy, we open up our telescope to our camera, we allow all the light through, or we let it pass through some filter, and we get an actual image of what this looks like, and we can see where different structures are. Following that, we have spectroscopy. And in spectroscopy, we're actually spreading the light out as a function of wavelength or as a function of color, which is demonstrated down here on the bottom. So this is kind of the visual portion of the spectrum, moving from blue at short wavelengths to red at long wavelengths. And when we take the spectrum of galaxies, we notice a few distinct features. So the first is what we call continuum emission. So this is just the underlying level of light that we see at all wavelengths. And this is mostly coming from all the combined lights of stars. Following that, we have emission lines. And so this is coming from excited gas. So we have an atom with an electron around it, and it's making very specific jumps between discrete energy levels. And so you get a very specific color photon. You get a very specific color or a very specific wavelength of light, which is denoted by these excesses here. And you can see these peaks in our spectrum. So we have a continuum with emission lines on top of it, and then we can also have the reverse, which is absorption lines. So the key here is that these emission lines provide us with an immense amount of information. First, they can tell us about the velocity of the material that we're looking at. So through the Doppler effect, if things are moving towards or away from us, these lines will be shifted towards the blue end of the spectrum or towards the red end of the spectrum. We call that redshift and blue shift, and we can use that to measure the velocity of this gas. And in addition, they provide tight constraints on what's happening within this gas. So each of these emission lines is caused by a different element or a different ionization state, and some of these are sensitive to the temperature, to the density, and so on. So we can use these as detective clues to figure out what's going on in this material. These are the ideas behind it, what's kind of the actual in practice. So what we do is we take an image of our galaxy, we point our telescope at it, and we isolate a very narrow region with a slit. We look at just the light coming from that portion of the galaxy that we're interested in, and then we take that light and we pass it through a spectrograph. We spread it out according to wavelength or according to color, and then we record a spectrum at each point along that slit. So we're getting a spectrum with that continuum and these emission lines at each point along our slit that we're looking through. Walking through this a little bit more, let's look at some of the most prototypical active galaxies that we have. So these are the new General Catalog objects 4151 and 1068. They're some of the most nearby and brightest active galaxies, so they're some of the easiest to study, some of the ones that have been studied the longest. And you can see here in these very nice images from Judy Schmidt that we have a bright center nucleus, which we have our AGN hiding down in there, and then we have these darker spiral dust lanes that are wrapping into the center, and then these bright blue and pink star-forming regions where we have lots of hot young stars. So from these images, we can get an idea of the distribution of material. We can see where things are. Let's go ahead and now take a spectrum. So we take the very center of the galaxy, and we spread that light out as a function of wavelength, and we get something that looks like this. So on the bottom axis, we have the wavelength going from blue to red, and then on the vertical axis, we have intensity, or just brightness flux. So it's basically the brightness of the light at each wavelength. So you see this underlying continuum at all wavelengths, and then you see these very specific peaky emission lines. So I'd like to draw your attention to a few features, because these are very important. We're going to look at these quite a bit. The first is that we have two types of lines. The first is we see narrow emission lines, which are intrinsically have a very narrow width, and then we have broad emission lines, which are much broader. And so just as the shift in these lines indicates the velocity of material, the width of these lines indicates the range of velocities present. So in the narrow lines, we have a small range of velocities present, and in the broad lines, there's a much higher range of velocities of all that gas. So some gas is moving much faster than other portions of gas. In addition, we split these up into what we call forbidden and permitted lines. Somewhat of a misnomer. Permitted are basically highly probable. They're very easy to make under a variety of conditions, and so we see them quite frequently, like hydrogen emission lines. And then we have forbidden lines, lines, which are essentially highly improbable. It's very difficult to create the conditions necessary to produce those lines in the lab, and the transition times are very long, so it's an unlikely line. So we call those forbidden emission lines because they violate certain rules of quantum mechanics. So we can go ahead and we can do some spectroscopic detective work, and we can figure out what is causing each of these emission lines, and each one is denoted by the element that creates it, and then its ionization state. And I'm going to focus a lot today on one specifically, which we call O3, which is doubly ionized oxygen. So an oxygen atom with 2 electrons removed, and it's producing this bright emission line here. And the reason we're so interested in it is because it is the brightest emission line. It has the highest flux, the highest intensity in the region of the spectrum that we're looking at, and so it's a strong tracer of this hot gas that we're interested in. So anytime I say O3, it means doubly ionized oxygen, a photon coming from that very specific transition. Final point I'll draw to is that some of these galaxies just have narrow lines, and other galaxies have both narrow and broad lines. And so this has led to this kind of type 1 and type 2 dichotomy, and through some detective work over decades, we put together this picture of active galaxy structure. So let me start off by saying this is a highly simplified diagram. Everyone has their own version of it, and this is also on a logarithmic scale. So as you move out, it's not a linear scale. These things get much further apart as you move out. So in the first case, we have our supermassive black hole down here in the center with this accretion disk of material around it that's injecting all this energy into the galaxy. And that energy propagates out until it intercepts some region of gas. And in this case, it intercepts gas that's close to the black hole, moving very quickly. And so it has a large spread of velocities. And so we call that the broad line region, because that's producing those broad emission lines. Then moving further out, we have gas that is moving more slowly. And so that produces those narrow emission lines. And so the overall picture that has emerged is that in type 1 AGN, you kind of have this view of the central engine. Your orientation of the galaxy in the center region is such that you can see down into these regions, whereas in type 2, there's something obscuring your view. It could be this disk of material we call a torus, it could be the plane of the galaxy, but it's basically blocking that region so you don't get those lines. Last point I want to highlight is that all of this inner region, so the black hole, the accretion disk, the broad line region, with the exception of the one image I showed before, all of that is generally unresolved. So it's a single little point source in the sky, and that makes it more difficult to disentangle what's going on in the system. So the narrow line region is the first scale moving away that we can actually resolve. We can actually measure its size on the sky and trace it across the sky in our images and spectroscopy. Now that we have this fundamental grasp of AGN and spectroscopy and imaging, we can go ahead and dive right in. So again, our motivation is that we want to see are these outflows actually powerful enough to cause to explain our observations. And we see outflows on a variety of scales and a variety of different gas phases. We're going to focus on the narrow line region because this lets us get fairly close to the black hole on the order of a parsec, or about 3 light years, moving out to scales of thousands of parsecs. And that's on that critical scale of galaxy voltage. It's basically spanning that full range. So if we're looking for something that might have an impact on the bulge, those are the kind of scales that we may be interested in initially. Finally, we want to go ahead and we want to actually measure the property of these outflows, which means we're going to be focusing on spatially resolved observations so we can map these out. So on the right here is an image of, again, NGC 4151, one of the most nearby and bright AGN that's studied a lot. We had a very nice talk just a few weeks ago from our newly minted Dr. Caroline Roberts about measuring a very precise black hole mass in this target. As you can see, all of us folks like to study the same couple of galaxies and call it a sample. So this is a ground-based image. You can see some of the large-scale structures, some of the spiral arms, etc. And just to highlight the power of these spatially resolved through the talk. So we have this center region emanating an immense amount of energy, going out, exciting this hot gas, and then driving it away. And in this case, we can actually spatially resolve it. We can see that the structure is clumpy, it's inhomogeneous, it's not uniform, and so that's going to play a very important role in what we do moving forward. So this image is incredible. How are we actually going to quantify, actually measure the properties of these outflows? So we're going to use our tools of spectroscopy and imaging, and the first thing we're going to do is we want to determine the gas mass and its velocity and the distance over which it's moving. And so we're going to use this to calculate a variety of what we call energetics. So the first is a mass outflow rate, which is essentially if you are standing at some distance from the center of the galaxy and you measure the amount of material moving past you, that's the mass outflow rate. And we typically measure that in solar masses per year. So for example, if you measure 1 solar mass per year, that's the amount of material that has moved past that boundary that you've drawn. Related to that are a variety of energetics, in this case the kinetic luminosity, which is dependent on velocity squared, and that's going to tell us about the impact of these outflows, whether it's just kind of a gentle breeze or if this is a hurricane that's actually going to cause a significant damage to the galaxy. And again, just highlighting the key that we're using spatially resolved spectroscopy and generally focused on is what we call global measurements. So they take everything of the narrow-line region within some radius and just add it all together, and we have a single mass, a single velocity, a single extent. And so we lose some of the information in between. And so what we want to do is fill in the steps. We want to actually take this and we want to break it up and look at it as we progress as a function of distance from the black hole. So the first trial of this was done by our very own Dr. Mike Crenshaw in 2015 on NGC 4151, and so I'll walk through their results briefly. So again, here on the left, we have that image of the narrow line region, and this represents our very narrow spectral slit from the Hubble Space Telescope. We take that light and we spread it out as a function of wavelength, and we get here these 2 emission lines coming from oxygen. And what I want you to note is that very faintly here, you can see this very narrow region. That's basically the rotation of the galaxy. So this is gas that's moving slowly and rotating. And on either side of the center, we see these very high red shifts and very high blue shifts, indicating large velocity deviations from rotation. And so this is that kinematic or that velocity signature of the outflow. And so we have material moving towards you on one side, material moving away from you on the other side, on top of this underlying rotation. So that gives you the first piece of what you need. We can fit these data and determine the velocity. The next piece we need is the mass. And the way we do that is we take an image of the galaxy just in the light of O3, just in the light of this hot, excited emission line. And so through a process known as photoionization modeling, which I'll talk about quite a bit later, you can basically create a model of your spectrum and determine how much gas must be there to produce that spectrum. So we map this out at each location. We combine the mass and the velocity, and we get the results for NGC 4151. So on the lower left here is the spatially resolved mass outflow rate. So starting at the center of the galaxy at 0 parsecs, moving out to 140 or several hundred light years, we see that it starts near 0, increases to a value of about 3 solar masses per year before dropping back down to 0. And so 3 solar masses per year might sound like a lot or a little, depending on what area of astronomy you work in. But the key is to compare it to a couple of key values. So the first is the mass accretion rate. And so this is the amount of material that has to be falling onto the black hole to produce the luminosity that we see. And it actually only takes a very small amount of material on the order of 0.01 solar masses in order to produce this luminosity. And so the amount of material being driven out at that location is over 200 times that. So we have this very efficient conversion, if you will, of a little bit of material in to a large amount of material being driven out. And in addition, this is about 5 to 10 times larger than outflows that are observed in the UV and the X-ray much closer to the black hole. And so this was the first indication that this could actually have a serious impact. This is something we need to look at more. And the final surprise is that this dashed line down here represents what you would get if you took the amount of mass that you saw at the center of the galaxy in that central region and allowed it to just propagate through at each velocity you measured. And so the big disparity here we take as evidence of what we call in situ acceleration. So rather than everything starting near the center of the galaxy and then traveling large distances, this radiation is moving out, exciting gas at its original location, and then pushing it. And exciting gas again, and pushing it at each distance rather than a steady nuclear flow. I'm not very good at interpretive dance, but I think you get the overarching picture here. So this was the motivation for our study. So then we set out some specific objectives. The first one is we want to quantify the mass, the velocity, and the energy of these outflows in a sample of nearby active galaxies. And the question we want to answer there are, do properties of the outflow scale with AGN parameters, such as the luminosity, the black hole mass, etc. The second one is, do these outflows have a significant impact on their galaxy? And so this could be in the form of evacuating material from the center regions. This could be terminating or triggering star formation and so forth. And the third and final one, which I'll explain a little bit more later, is we want to compare what we've done to previous techniques. So those global techniques that add everything together, and see if we can find a happy medium and basically say, can we reduce the problem? Can we get away with less data or less modeling? With these objectives, we need a sample and we need observations of that sample. So our observations are going to be coming from two places. The first is from the Hubble Space Telescope using the Space Telescope Imaging Spectrograph. And so here's an image of HST on the left. And the reason we're using HST, again, is it's in space well above the atmosphere, and we can isolate very specific regions of these outflows. We can get down to spatial resolutions on the order of 0.1 arc seconds, which for these nearby AGN is scales of about 5 to 20 parsecs or a little bit larger. And so we're able to get a very fine view, but we have a very narrow slit, so we don't get a lot of light. So as we move further out into the galaxy, we tend to lose the emission lines that we need for modeling. And so we took advantage of some supplementary observations with the Apache Point Observatory, shown over here. This is the 3.5 meter telescope with a little person there for scale. And so in that case, we have a much larger slit, a larger aperture. We get a lot more light, but we don't get as fine of spatial resolution. So we're basically getting big chunks of the galaxy, but we can extend our observations out much further. So it's kind of the best of both worlds. We have a zoomed in view of the center, and then we have a view of the large scale galaxy at large. And here's an example of an image of one of the galaxies, just showing the size and position of the HST slit in green, that very narrow slit, and then the red slit from APO much wider, and the blue from a third set of observations. So in order to construct a sample, we started with the results of our very own previous grad, Dr. Travis Fisher. And what he and colleagues did was essentially look at the HST spectra of pretty much every nearby active galaxy, about 60 galaxies that already had the data we needed, and they tried to isolate ones that had these strong kinematic signatures of outflow. So they found about 17 or so that had some signature of outflow of this fast-moving gas. And then from there, we narrowed down the sample based on our specific requirements, which require more spectra and images, and we ended up with 6, including NGC 4151. And I'm going to talk a lot today about the results for 2 of these galaxies. So the first is Markarian 573, and the second is Markarian 34. Here's some nice images of those, showing again the bright center regions and this hot excited gas. And the one number that I want you to pay attention to is that the luminosity is larger than it is for 4151. So in the case of Markarian 573, it's injecting about 15 times more energy out into the galaxy. And in the case of Markarian 34, it's another step above that. So we're looking at these outflows as we go to these more powerful, more luminous active galaxies. And so the results for these 2 targets have been published in 2 papers in 2018. And so I'm going to follow along with the results of those papers. So I breezed over the analysis for the results for NGC 4151. Now let's look at it in more detail for our study. So the first thing we're going to do, here we have an image of Markarian 573, again, just in the light of oxygen 3, looking at just that hot, excited gas. And here we have the HST slit that got our observations, and we're going to extract a spectrum at each point along that slit. Once we've done that, we're going to fit the emission lines with Gaussian profiles in order to determine their shifts, their red shifts or blue shifts, and get the gas velocity. That gives us the first portion of what we need. After that, we're going to model the spectra using the photoionization code Cloudy. And so this is a code that's very powerful. It's been developed over the course of about 30 or so years. For the students who have taken the ISM class here, they're very familiar with it. They're not always so fond. They kind of described it like this. But I think it's an immensely powerful and interesting program. So we're going to model those spectra, and what that's going to provide us with is the amount of mass at each point along this slit. And here's where all the magic happens. We're going to take that mass, and we're going to take the amount of flux that we get, the luminosity from that O3 line, and get a scale factor. Basically, for every unit of light I see, how much mass has to be there, and that will let us convert from flux into mass. And then finally, we have all this other gas out here that's outside of our spectral slit. We use our O3 image, and we break it up into little segments, and we can measure the total flux at each distance. then we use that multiplicative scale factor to go from flux to mass. And with those, we can calculate the mass distribution and these mass outflow rates and energetics that we're so interested in. So let's go ahead and walk through this a little bit. First, we have our spectra, again, looking at intensity versus wavelength. And really what I just want you to take away here is that we have a lot of different emission lines from a lot of different species. So for example, we have O1, which is neutral oxygen, takes very little energy to produce that emission line, alongside with things like iron 14. So iron with 13 electrons stripped off, it takes hundreds of volts of energy to produce that line. And this is all coming from the same location. So we have very low energy lines, very high energy lines, and we need to be able to explain all of these if we want to accurately measure how much gas is at that location. So again, highlighting the O3 lines here, we're going to fit those lines in order to determine the kinematics. In this case, there are actually two of each emission line. And so the one to the left here is consistent with rotation. It's moving at a slow velocity. Whereas here, this line, which is redshifted, which is why I've colored it blue, just to keep you on your toes, is moving at a much higher velocity, and so that's indicative of this outflow. So at this particular location in the galaxy, we have gas that's rotating and gas that's outflowing. So there's some complex things going on. So we do this process at each point along the galaxy, and we end up with the gas velocities. So this is the first portion of what we need to calculate all of these outflow parameters. So here we're looking at the results from Markarian 573 and Markarian 34. And in each case, we're looking at about the inner 1.5 kiloparsecs, so the inner 1,500 parsecs. I'd like to draw your attention to a few things. So the first, these red lines are just kind of a qualitative curve of what you would expect for normal galaxy rotation. So gas that's just rotating around in the galaxy, mostly undisturbed. And we see these very large deviations from that we fit with these green lines here, and this is that kinematic or that velocity signature of outflow. So you can see near the center of the galaxy, the velocity is very low, it increases to some maximum value, and then it decreases from there and turns back into rotation. Finally, in the case of Markarian 573, everything out to some distance is basically the outflow, and then it just transitions into rotation. Whereas in Markarian 34, we have both at each location, which is a little tricky to explain because we have gas that is just rotating around in the galaxy, as well as gas flying out at 2,000 kilometers a second, roughly at the same location. We have to be able to explain all that. So finally, these velocities are all the observed values. Whenever we measure the velocity from our spectra, it's just the piece of velocity that is in our line of sight. So if something's moving perfectly along your line of sight, you measure 0, even though it may be moving very quickly. And so we model the galaxies, basically model the host galaxy in order to figure out its orientation on the sky, and then deproject that velocity to the true value. And so in each of these cases, the maximum values end up to be about 1,500 and about 2,000 kilometers per second. So those are the kinds of velocities that we're dealing with here. This is the first portion of what we need to determine the velocities. Now we need to determine that gas mass. So the key to our process is that we're using multiple cloudy model components. And what I mean by that is rather than assuming that all the gas contributing to that spectrum is at a single density or a single temperature, we're allowing for a range of conditions. So as you saw from that image, this material is very clumpy, very irregular, very inhomogeneous. And so within the region that we're extracting our single spectrum, there may be a range of conditions present. Again, we need to be able to account for all of that if we want to determine how much gas is actually there. So what we do is into Cloudy, we give it a series of inputs, and then it will predict the output spectrum. So these inputs, the first thing is the spectral energy distribution of our AGN. It's basically the number and the energy distribution of photons that are coming from the AGN. So how much energy and at what wavelengths is intercepting this gas and exciting it to produce these emission lines. In addition, we have the abundances, so how much of each element are actually in the gas, and then anything else that's in the gas that may affect the heating and cooling. So in this case, that's usually dust and the corresponding depletions. Things like to get locked up into dust grains, and then they can't contribute to the heating and the cooling of the gas. Once we think we have all these parameters nailed down, we go ahead and we run models that are constrained by the geometry of the system. And so what I mean by that, here this is the ionization parameter equation. Simply, U is the level of ionization, so a higher U means more highly ionized, more highly excited gas. And that's equal to the number of photons hitting that gas divided by values to make it a flux at a distance and density and speed of light to make it unitless. And essentially what this is at some distance, it's just the ratio of the number of photons to the number of gas atoms. So if it's 1, you have 1 photon for every gas atom. If it's 10, you have 10 times as many photons as you do gas atoms. And so depending on what the ionization parameter is, that will determine what our model spectrum looks like. So finally, we want to go ahead and take our model. So we take these multiple components that we have, which we very uniquely named high, medium, and low, and we take all different fractional combinations and see, okay, what range of conditions for these different components can reproduce the emission lines that we see. And so here's an example of that. We're looking at the model value divided by what we call the d-redden, so the data corrected for extinction. And so here we have each emission line, and if our model and the data agree exactly, they would be 1, because we'd have the exact same value. When you divide those, you get a ratio of 1. And then we set an overall region where all of the emission lines, regardless of anything, have to agree within a factor of 3. And so I'll just highlight a couple of these lines. The first is the O3 lines that we're going to use to convert from flux to mass. And so we set very strict criteria there. They generally have to agree within 10%, at the most 15 to 20% if needed. And then we have other lines that are sensitive to the density, sensitive to the temperature. And so we want all of those to be as well constrained as possible, again, in order to get an accurate gas mass. So we have fits like this at each point along our slit. And of course, all of them look this good, so you don't have to ask me more questions about it later. Now, of course, there are sometimes deviations, right? This is science. And when we see those, that tells us something interesting. It means there's something we're not quite capturing. So this is a very iterative process. This is where a significant amount of your time slips away to, but you learn a whole lot in the process. So we take these models. The key is these models give us the parameters that we need to calculate the gas mass. So again, we come back to this image of 573 in the light of oxygen 3. First thing we want to do is calculate the mass from our spectra. So that's equal to the actual luminosity of the hydrogen Balmer line, so one specific stable emission line, divided by the flux that our models predict. And that gives you the area of all the emitting clouds. You take that area and you multiply it by the number of particles per unit area, which comes from our models. That gives you the total number of particles. And you multiply it by the mean mass per particle, that gives you the total mass. So at each location along this slit, we now know the mass of this ionized gas. Then we can go ahead and derive this scale factor. So basically, for a given mass at a given flux, for some density, what is that conversion factor? If I see X number of photons, what is the Y number of atoms in order to get the gas mass? And finally then, we add up the flux in each of these annuli, and we use our scale factor in order to get the mass at each distance. And really the takeaway point here is that the mass is dependent on the luminosity and inversely proportional to the density. So if we see a larger luminosity, it makes sense that there's more material there, but it's inversely proportional to the density, which means as you turn the density up, for a given luminosity, the mass actually goes down. And so if you have two clouds that both have the same luminosity, one is 10 times as dense, it actually has 10 times less mass. And that's because the process becomes much more efficient. Those electrons can find atoms and recombine and emit photons at a much higher rate. And so this is very important when we're trying to calculate an accurate gas mass. So this is the mathematical representation. Here's the final visual representation before I get to the results. Again, here we have this image. We measure the flux in each of these rings, which is the total flux at each distance. And we use our scale factor that lets us go from flux to mass, and we get a mass distribution. So here at the center of the galaxy, starting low and then increasing. In blue, we have the data from our, we have the models from our Hubble Space Telescope data. And then as we moved further out, there were basically insufficient emission lines to actually model. And so there, we kind of pieced it together with our data from the Apache Point Observatory in order to follow the outflow out through its full range. So we'll take this on either side and we'll fold it together, make a single radial profile. And here's our first key result. So this is from Markarian 573. What you see here is distance from the nucleus versus the total mass, and distance from the nucleus versus the mass outflow rate. You can see down here the result for NGC 4151, and you can see in this case we have a much larger amount of mass extending to much larger distances in this more luminous target. However, we look at the mass outflow rates and we see they both rise to peak values of about 3 solar masses per year before decreasing. And again, this overall shape has to do with the velocity profile. We found that the velocities start very low and increase to higher and higher values and then decrease back towards rotation. And so you get a higher mass outflow rate when you have a very high velocity and then decreasing from there back towards 0. This is for our first target. For our second target, Markarian 34, it's a little more complex. In this case, I have 2 sets of data points. And the first in red is basically the total. And so this is if we add up all the gas that we see. However, as I mentioned, we saw that the kinematics, the velocities, told us that there's some gas outflowing and there's some gas in rotation. And so we can actually separate that out and measure just the fraction that's being pushed out, which is really important. Otherwise, we would tend to overestimate all of these quantities. And again, we see that the mass outflow rate just kind of reaches this 2 to 3 solar masses per year. So kind of what's going on here? These targets are getting more and more luminous. They have more and more mass, going from about 300,000 solar masses up to 3 million solar masses. So this is a lot of material. And yet the mass outflow rate is all about the same. And so where this starts to spread out is when we look at the energetics. So if we look at how much energy is being carried, now we start to see this big separation with NGC 4151 down here and then increasing. And this is because the energy is proportional to the velocity squared. And so we have more mass moving at a higher velocity, and so it carries significantly more energy. It has a larger punch with it. And so this is where we start to see things separate out. So this is a lot of results, a lot of information contained in these diagrams. What's the overall picture here that we see so far? So now, these are the first 3 AGN that have spatially resolved mass outflow rate profiles. And what we see is that the total mass in the outflow, its velocity, and how far it reaches into the galaxy all seem to be correlating with luminosity. So a more luminous AGN injecting more energy is able to drive larger, more massive outflows. However, we note that the peak mass outflow rates are all about 3 solar masses per year. Interesting. And so then the question is, how does this compare with what's been done before? So we want to put our results in the context of other studies. And so as I mentioned earlier, previous studies have focused basically on what we call global techniques, taking all the mass in the entire narrowline region at a single velocity and getting all these properties, these mass outflow rates, these energetics. And so the question is, did we do any better? Do we see any differences? So these global techniques have been applied to many, many galaxies. There's lots of them in the literature. However, uncertainties within those global estimates are uncertain, if you'll forgive the pun. Essentially, it's very difficult to know how accurate these answers might be because we don't know how these properties change as a function of distance. So what we want to do now is take our results and we want to compare them to what's been done previously. So the first thing I'll focus on are these global techniques. And so again, this is adding up all the mass and assigning it a single number. So here we have Markarian 573, and one of the most commonly used techniques is what we call a geometric technique. And so what you do is you figure out the area of your narrowline region that's emitting this light, the narrowline region that's emitting light, and that gives you some area, and multiplying it by the fraction of that volume that is filled in this bicone, along with the density and velocity, gives you a mass outflow rate. And so in this case, we get a result of about 65 to 6,500 solar masses per year. That's large. And so as compared to our 3 solar masses per year, this is orders of magnitude, factors of 1,000 larger. And so this is a little bit alarming. And the key to this process is that the mass is geometry dependent. So depending on how you say, okay, I'm going to look at this and I'm going to draw this region and I'm going to say that that volume is filled, that will determine the mass independent of other properties of the observation. The second technique is a luminosity-based technique. And so for our modeling, we're modeling all these different emission lines. In this case, it's basically a scaled down version where we take the luminosity of a single emission line at a single density and a single velocity and just convert the number of photons to the number of gas atoms using a very simple scaling relationship. And so in this case, we get an answer about 5 to 35 solar masses per year. So that's much closer agreement, but still somewhat overestimated, and we don't know how that changes as a function of distance. But the key here is that the mass is being traced by the emission lines. We're actually using a physical observable to calculate the mass. So in the case of a system like this, if we had 3 AGN with the same volume that we think is outflowing, but 3 different luminosities, this first technique would give the same outflow rate for all of them, whereas the second technique would be able to separate them out because it's using a conversion between luminosity and mass. And so the takeaway here is that we want to at least focus our future efforts on the luminosity-based techniques, just because they have smaller intrinsic uncertainties. So we don't necessarily want to go this route. We have our spatially resolved results. Now the question is, can we find a happy medium? Can we still derive these properties as a function of distance from the black hole, but can we simplify the process down? And so there are 2 pieces to this. The first is we might be interested in using data that has a less extensive wavelength range, and so we maybe only have 1 emission line. And we're also interested in the fact that do we absolutely need photoionization models, or can we get away with just converting the luminosity of a line into mass? So even if we just have a spectrum with a single emission line and an image, that will tell us still the velocity of this gas. It'll tell us its extent from the center of the galaxy, and we can measure its brightness. So then the only thing we need is the gas density. And so there are two techniques that are commonly used to estimate the gas density when you don't use modeling. And so the first is using emission lines that are sensitive to the density of the gas. In this case, sulfur 2. So these are two lines where their relative strengths change as a function of density. The other case is just assume a constant density. You pick some value that has some motivation and you just assume it's the same everywhere. And so we also tested a number of other techniques. These are the two that I'm going to focus on today. And so what we want to do is compare these to what we're calling our benchmark results, the best that we think we can possibly do, and let's see if we can simplify this process and still get back the same answer. So first, here's the result for NGC 4151. Down here in black is our result from our modeling, and in blue here is the result that you get if you calculate the gas density from sulfur 2. And so you can see that in this case, it overestimates the mass and the mass outflow rates by about a factor of 6. So not factors of 1,000, but still an overestimate. And you notice that the shapes are very different. So we're under and overestimating at different locations. So certainly more promising, but still some issues to be worked out. And then the other case is assuming a constant density profile. And so in this case, we have three different densities of 10 to the 2, 10 to the 3, and 10 to the 4. So 100, 1,000, and 10,000. And then we have the ratio of the mass that we get from that technique relative to our models. And so basically the takeaway here is that a density of 100, or 10 to the 2, is the most commonly used value in the literature. And what we see is that this tends to overestimate the mass by about a factor of 60 in this case. So fairly significantly overestimating. Our data are actually down there on the plot. If I go ahead and zoom in on just that region, you can see that not only is a density of 10 to the 2 too high or 10 to the 3 too high, 10 to the 4 is closer, but again, the shapes don't necessarily match. So that just means that the density is not constant as we move out, which we knew from our photoionization models. We knew that the density is a function of distance. So again, let's kind of summarize these results and condense down the main points. The first is that global techniques that add everything together that have been the primary method used we seem to do, estimating the gas density without the use of photoionization models is very difficult. Finally, a key point that we want to note and highlight is that the most commonly assumed density actually provides the largest discrepancy. And so this one temperature, there's a range of conditions present, and we need to account for that. Ultimately, we want to build a larger sample. So as I mentioned, we've done this now for 3 galaxies. We had 3 more in our original sample. We were hoping to find a simplified technique that we could then very quickly process through these. This is science. That doesn't always happen. We could not find a simplified technique that we were satisfied with. And so we're going to continue to process some of these galaxies in this case-by-case manner. And so we have a larger sample of 6. There's additional data in the archive that we've located now that had been filled in, and we've also submitted proposals to get even more data to ultimately, in the long term, with more graduate students, build a sample of about 10 to 30 galaxies. And what that's going to let us do is parameter space. So we've looked, but it's still only meaningful statistics, and so we can probe through a variety of parameters such as supermassive black hole mass, the luminosity AGN, the size of the galaxy bulge, and so on. And finally, then we can actually compare this with the star formation in the galaxy, see if we see this feedback going on, and extend this to higher redshifts. And that's really the key, because as we move to larger distances, earlier in the universe, we have more powerful, more luminous AGN, but they're also less well resolved. They're much smaller on the sky. And so if we want to go ahead and measure their mass properties and their outflow rates, it's going to be very critical to understand what happens when you just estimate with a single value and things that are kind of barely resolved. And then finally, if you're not overwhelmed enough, everything that we've done today is a single gas phase. This is the gas that is coming from the optical emission line gas, also portions of the UV. However, there are other gas phases that we're not accounting for here. So gas that's very, very highly ionized in the X-rays, much colder gas in the molecular gas, and we sort of need to add up all these layers to create a complete multi-phase picture of mass outflows. And so we've thought about this quite a bit. Here's an example just showing that it is doable. So again, here on the left is Markarian 573, and on the right shows X-ray data from a nice paper by Alessandro Paggi, and just showing that we can actually map changes in the X-ray data as we move across the narrow line region. So with that, I'll go ahead and wrap up. First, we have now produced the first 3 spatially resolved mass outflow rate profiles for AGN, and we're now convinced that using spatially resolved observations is essentially required if we want to accurately probe these parameters and see where the feedback is happening. We find the peak mass outflow rates are all about the same, 3 solar masses per year. However, the luminosity or the energy in these outflows kind of reaches these benchmark results around this 0.5% value that's needed in order for effective feedback, in order for these outflows to have a significant impact. And so for these galaxies, it may be sufficient to kind of clear the inner bulge, the innermost regions of the galaxy, but it's certainly not clearing the entire bulge. But again, these results are going to be important as we push to higher redshifts and we look at more powerful active galaxies and we try to find that transition phase where we're actually able to completely clear a bulge, for example. Finally, we see that the mass outflow rates are all about the same. However, we do see a scaling of the radii and the energetics with luminosity. But all of this is very dependent on using photoionization modeling to accurately determine the gas mass. We're convinced now that that is the way that we need to move forward. And finally, we'll ultimately go ahead and extend this to other gas phases to try to build up this full picture of feeding and feedback in nearby active galaxies. And with that, I would be happy to field any questions.
Those that were on the dissertation committee, please save questions for later. I will just make a comment that knowing Mitch, I should have guessed that simplified techniques was not going to be good enough. So anyway, that's the way it turned out. So yeah, go ahead.
Please.
No offense to Mike or anybody else with extragalactic talk. Not only is your work super probably the first. I'm curious about. Are you observing, like, for example?
Certainly. So one of the things that we did is we wanted to take advantage as much as we could with existing observations. And so for the majority of these are archival data from Hubble Space Telescope, which I should have mentioned. And so these are spectra that were gathered when I was just a few years old for many of these targets, but they haven't been used in this way before. So the first thing we did was say, okay, let's go to the archives and see which ones have the spectra and the images that we already need. So gathering those spectra and images is not terribly expensive. So the spectra and the imaging together take about 4 HST orbits. And then from there, we've been working towards building this larger sample based on targets that have some of the data. So for example, ones that have just a spectrum but not an image, or vice versa, and saying, okay, let's fill in those pieces in order to build a much larger sample. So again, yeah, first thing was take advantage of the archival because they're already there, ready to go. And now we want to try to build up, making the case that many of the data already exist, but we just need this extra little piece, and then we'll be able to do this for a much larger sample. So yes, HST certainly does have better spatial resolution. It ultimately comes down to having the same scale factor. So in this case, in the inner regions, we were able to create full photoionization models to determine a flux to mass scale factor. since we had insufficient emission lines in the HST data out there, we used that same scale factor and then estimating the density through a variety of techniques. And so the reason the errors are the same is because the fractional uncertainty in the scale factor is the same. And so in this case, even though there was a larger uncertainty in the density, the emission lines were very strong and had smaller uncertainties. So they kind of all conglomerate to make something that's roughly about the same, at least visually. But the fractional uncertainties are slightly different as you move out. So you have more precise measurements, but less constrained.
Can you go to the similar graph that has all three? All right, so 3 solar masses per year. Struggling to understand drops off in both directions.
That is,
What's going on?
all right, give me another 45 minutes now. So the first portion of that, in this case, the overall shape, again, is due to the velocity. So the velocities, the outflow velocities seem to start near zero, and then they rise to some peak value. And then due to probably a combination of enclosed gravitational potential and reduced ionizing flux, at some point you cannot drive the gas as efficiently, and so the velocities again decrease to zero. Now, as you touched on excellently, again, this is the optical emission line gas. So one possibility is that this material is driven and expands, becomes less dense, and transitions into the X-rays. And so if you were to continue this with other gas phases, you would actually see it continue to rise or flatten out, but it's disappeared from our observations. It's moved into the X-rays, and so we need those data to probe it.
Not disappearing and energy's not disappearing.
Yes, no, it is not disappearing. It's going
Better
somewhere.
about this whole field.
One of the interesting things, ionized gas mass, we're continuing to strip off that gas as we go.
Right, so you can, for example, based on the mass we see and the mass outflow rate, you could say, okay, the evacuation time scale is about 1 million years to get rid of all this gas. However, there's a big reservoir, most likely, which we're confirming with some of these targets now with ALMA, of molecular gas. And if you're just continuing to ionize gas off this giant reservoir, then the evacuation time scale goes up. You have much more material that you need to clear out.
Of the peaks just have
To first order, yes.
first order.
Yes.
The plot where you compared the different techniques well, when you had the actual plot that tracked
This one?
yes.
The sulfur 2?
Yeah. So sulfur 2 you said is physically dependent on the density. If that's the case, why would it show such a discrepancy between that and photoionization results?
Right, so in this case, the sulfur 2 lines are only probing the density of one specific gas phase. And so in this case, the sulfur 2 lines are fairly low ionization, so it'd be somewhat comparable to, say, our low ionization cloudy component. And it's not accounting for the other gas at more highly ionized phases. And so when we add all that together, it turns out that it reduces the total mass. So basically, sulfur 2 is giving us one piece of our 3-piece puzzle in the optical. And what happens is because sulfur 2 is a low ionization line, it underpredicts the density as compared to kind of the mass-weighted mean, and so it overpredicts the total mass. Yes, so we're doing the multi-component modeling for each spectrum at each radius individually, and then calculating the mass at each of those locations, and then using that to get our scale factor. So yeah, it's not a single model. We're modeling this at each and every spectrum that we have. So it turned out that the average scale factor, the deviation in that, so the scale factor does vary, but the deviation was on the order of, say, 10%. And so there was no particular reason to assume that any point was any better than any other point. And so because we saw it was relatively constant, we adopted a mean in that case. Had we seen some trend with radius, then we absolutely would have had to include that. to the AGN. And then, of course, in the ionized gas, we see the amount outflowing. And then as you move further out into the bulge, you're enclosing more and more mass through the stars and everything. And so we have done, at least for one of these objects, led by Travis Fisher, kind of a radiative driving study to look at the balance between radiation force pushing on this gas versus gravity trying to pull it back in. And so that's kind of one of the balances that you eventually may reach. Maybe part of the reason we see that turnover in the velocities, because as yes.
General idea. Or more.
So in terms of the amount that's accreting onto the supermassive black hole, it's significantly less. So for 4151, the ratio of outflow to inflow reaching the black hole is a ratio of like 200. So you have very little material going in as compared to what's being blown out. Now, however, that's just the material that's reaching the accretion disk. So you may have a much larger mass inflow rate, which then there's some connection between the inflows and the outflows, and all that material doesn't make it in. So particularly targets with bars and so forth, that's something that you have to measure very precisely.
Turn the AGN on.
One last one.
Did I miss that? Like,
No, you didn't. So we've been trying to answer that one for some time, and that's still a piece that we're working on. So I mean, the overall trend of increasing and decreasing, we can kind of understand in terms of we have an immense amount of luminosity that as you go out, divides by. On here?
Sorry, you had dotted lines.
Oh, for the velocity profiles, yes.
So there's lines supposed to go through those points?
To an extent, yes.
Status of extragalactic.
There is a flux.
Except we didn't talk on a log scale.
That's right.
Well, you get points for that.
There is a flux weighting dimension to this. I'll throw that in there. Not all points should necessarily be weighted equally.
It's not a fit.
This is a very inhomogeneous system, right? These outflows are not necessary. And so, yeah, so choice of velocity law. So we provide all results necessary to rescale should you choose a new velocity law.
So it's not a fit.
Further away than the stuff you look at. So it's harder to see what's going on. These things you could probably visit if you had a nice spacecraft.
I've been seeing these talks for 19 years, and at this point, I would have thought that some minds would go through some points. But I guess another 20 years, we'll be very good.
There's probably some stars. There's probably some stars in the outflow that's messing things up.
So this is not a fit. The rotation stuff. But Vina, going from large scale rotation for separating out outflow. Yeah,
in the back.
So Vina's going to fix it all.
in a few years,
That's right.
a couple years, you hear all about that.
Well, it's under control.
It's under control.
Any other
Thank you so much, everyone, for.
thank you.
I do want to throw in one last note. After the committee meeting concludes late this afternoon, if anyone is around and would like to join us, we're probably going to head over to the Westin Sky Lounge around 4:30, 5 o'clock.
hey.
So please feel free to join. We'll probably meet somewhere.
Yeah, just dissertation committee. Let's take like a 5-minute break and do the real work.
Thank you, sir. Thank you so much for coming. Forgot to sell me at the end there. Jeez, thank you.
What?
Way to sell everything at the end. Thank you.
Yo.
That was so great.
Can I
appreciate
take a
that.
selfie with you?
Please, please. Thank you very
I
much.
just wanted to say thanks for making the proper pop culture reference. I've seen way too many Avengers references.
Yeah, I had to get that in there.
You made the right one.
Thank you. Can you hit the lights on your way out, Dan? Yeah, sure. Thank you.
Whoa, my arm is on.
Whoop.
Can you do it?
My hand's shaking like a devil. Ah. I get the bottom right here. Oh god, that's probably gonna check if that's blurry. My hand's like doing this.
Good job, man.
Thank you very much. Appreciate it.
It's all right.
Thank you for your message. I appreciate it.
Great. I was in for that a lot longer than a lot of other.
I'll take it. Yeah, I'll take it. I'll take it.
You did it, buddy.
Did it? Yeah.
I know.
2 weeks. Yeah.
I know.
It's all good. It was easy. It's fine. I just blacked out for the whole thing. Yeah. Thank you. Oh my god.